Okay, so we're going to discuss section 4.4, which deals with indeterminate forms and L'Hopital's rule. Okay, section 4.4, they talk about many different indeterminate forms. We're going to only touch on 2 of them. So there are more in the textbook. We're going to only look at 2 of them. Okay, so we're going to start off by discussing this function. Let f of x equal the natural log of x over x minus 1. Okay, this function is not defined at x equals 1, right? When you plug 1 in, you get 0 in the denominator. But we're going to be concerned at not what's happening at 1, but what's happening near 1, right? That's what we're going to be concerned with. What's happening near 1, okay? If we directly substitute x equals 1 into the function itself, right? If we actually take 1 and plug it into the function, f of 1 is equal to the natural log of 1 divided by 1 minus 1, right? So that gives us 0 over 0, right? When we substitute a number into the function and we get something of the form 0 over 0, this is called an indeterminate form. An indeterminate form of the type zero over 0. Okay. Another type that we're going to look at in this section is if we get something of the form infinity over infinity. Okay, and I'll explain what that means a little later on. So before, when we were trying to evaluate limits, and we had something like this, right? The limit as x approaches 1 of x squared minus x over x squared plus x minus 2, right? What we would try to do is we try to factor the numerator and denominator, right? Take out an x here, x minus 1 is left, and factor the denominator, x plus 2, x minus 1. And when we factor that, we can actually cancel out those factors, and then we could use direct substitution and plug 1 in to find the limit, right? That doesn't always work. Looking at this example with natural log of x over x minus 1, we can't factor and do direct substitution. So we have to use something different. How do we find a limit here? Well, we're going to use what we call L'Hopital's rule, okay? L'Hopital's rule. Suppose the functions f and g are differentiable and f prime of g does not equal 0 near a, except possibly at a. Suppose that the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0. Well, if they both equal 0, you end up with this indeterminate form that I talked about a little earlier with 0 over 0. Or the limit as x approaches a of f of x equals plus or minus infinity, and the limit as x approaches a of g of x equals plus or minus infinity. That gives you that other indeterminate form where you end up with infinity over infinity or negative infinity over negative infinity. So then, if you have that indeterminate form, right, 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, provided that this limit exists or it is infinity or negative infinity. Okay, in order to use L'Hopital's rule, the conditions must be satisfied. Okay, L'Hopital's rule is valid for one-sided limits. And can use L'Hopital's rule repeatedly, so you can continue to use it until a limit is obtained. Okay, so now we're going to look at a couple of examples dealing with L'Hopital's rule. So first example, let f of x equal the natural log of x over x minus 1. Find the limit as x approaches 1. So we're trying to find the limit as x approaches 1 of the natural log of x over x minus 1. Right? So before you use L'Hopital's rule, it has to be an indeterminate form, meaning it has to be 0 over 0 or infinity over infinity. Right? So we already saw if you plugged 1 in, natural log of 1 is 0, right? And you plug 1 in here, 1 minus 1 is 0. So it's an indeterminate form. So we can go ahead and use what we call L'Hopital's rule. And I'm going to go ahead and put this L above the equal sign to say that I'm using L'Hopital's rule here. And L'Hopital's rule says that the limit as x approaches 1, I can basically take the derivative of the numerator and the denominator. So the derivative of the natural log of x is 1 over x, right? And the derivative of x minus 1 is simply 1, right? Now that I've used L'Hopital's rule, I can actually do direct substitution, right? I can plug 1 in. So wherever there's an x, I'm going to put a 1. And so my limit is 1, right? So moving on to example 2. Find the limit as x approaches infinity, right? As x approaches infinity of x e to the x over x squared. Well, as x approaches infinity, as this x value gets infinitely large, so does e to the x, right? It approaches infinity as well. And as this x value gets large and you square it, it also approaches infinity. So it's in the indeterminate form infinity over infinity. And so now we can use L'Hopital's rule. So I'm going to go ahead and put an L over it saying we're using L'Hopital's rule. And so you take the derivative of the numerator. So the derivative of e to the x is e to the x. The derivative of x squared is 2x, right? Well, notice here when I go to try to evaluate here, I still have an indeterminate form, right? As x approaches infinity, e to the x approaches infinity. Same thing here, as x approaches infinity, 2x approaches infinity. So I still have indeterminate form, infinity over infinity. So I'm going to go ahead and use L'Hopital's rule again by taking the derivative of the numerator and the denominator. So the derivative of e to the x is e to the x, and the derivative of 2x is simply 2, right? And so now, what is happening to e to the x as x approaches infinity? Well, it's approaching infinity. And what's happening to just 2? It's a constant, right? So it's simply 2. So infinity, an infinitely large number divided by 2 is still infinitely large, right? So the limit here is infinity. So continuing with example 3, right? So first you need to determine if you can even use L'Hopital's rule. So if I plug 0 in, that's sine of 0 minus 0 over 0 cubed, which gives me back 0 over 0, right? So that is indeterminate form of type 0 over 0. So we can use L'Hopital's rule here. So I'm going to go ahead and write my original problem. And I'm going to go ahead and use L'Hopital's rule, right? Because it is of this form 0 over 0. So I can take the derivative. So the derivative of sine is cosine. Derivative of minus x is minus 1. The derivative of x cubed is 3x squared, right? So check the form. If you plug 0 in, you end up with 1 minus 1 over 0, which is 0 over 0. So because I end up with that indeterminate form, I can go ahead and use L'Hopital's rule again. Well, the derivative of cosine of x is negative sine x, and the derivative of negative 1 is 0. You end up with 6x. When you plug 0 in, you end up with another indeterminate form, 0 over 0. So we have to use L'Hopital's rule again. So the limit as x approaches 0. I end up with negative The derivative of sine is cosine, right? The derivative of 6x is simply 6. And now I can do direct substitution. So that's negative cosine 0 over 6, which is negative 1/6, right? So the last example, calculate the limit as x approaches pi from the left of sine of x over 1 minus cosine of x. So you need to determine if it's indeterminate form, right? And so you plug in pi, so that's the sine of pi over 1 minus the cosine of pi. Well, the sine of pi is 0, right? 1 minus the cosine of pi is negative 1. So you end up with 0 over 2. This is not indeterminate form, right? So you cannot use L'Hopital's rule here. You actually just use direct substitution. And evaluate your limit that way, right? If you try to use L'Hopital's rule, you're going to get an answer, possibly, but it's not going to be correct because it originally wasn't in that indeterminate form of 0 over 0 or infinity over infinity. And so that sums up indeterminate forms that we're going to discuss and L'Hopital's rule for section 4.4.